Okay, let's dive right into this explainer. We're going to explore the really fascinating evolution of concrete, from a basic rule of thumb recipe into a highly precise science. When you look at the skyline of any major city, you're basically looking at a monument to concrete. I mean, it's by far the most widely used construction material on Earth today. But the way we actually put that material together, that has undergone a massive paradigm shift that anyone interested in engineering or the built environment around us really needs to understand. It brings up a really critical question. Are you just baking concrete, or are you engineering it? Look, it's incredibly easy to just make concrete, but making truly durable, highly efficient concrete, that requires a fundamental shift in how we approach the mix. Are you just blindly throwing ingredients into a mixer and hoping it's strong enough to hold up a skyscraper? Or are you calculating exact statistical probabilities to guarantee performance? Today, we're comparing the traditional rule of thumb approach, which is the nominal mix, directly against the modern, mathematically driven design mix methodology. We'll see exactly why engineering codes have completely evolved, break down what each method actually entails, and uncover why one method is getting left in the past while the other is literally building our future. Section 1. The Concrete Conundrum. Engineering the Future. As noted in MS Shetty's engineering text, the difference between good and bad concrete lies almost entirely in quality control and how we handle the materials. There's this old saying in the industry, broken stone, sand, and cement make good concrete. But the exact same proportion of broken stone, sand, and cement can also make terrible concrete. It's a bit of a terrifying reality, right? The end product depends just as much on your methodology and job site quality control as it does on the raw materials themselves. Let's move on to Section 2, the nominal mix, the basic recipe. Think of the nominal mix exactly like baking a cake from a box. It's a simple, rigid, prescribed recipe. You might recognize the classic 1-2-4 ratio, 1 part cement, 2 parts sand, and 4 parts coarse aggregate. It's a total one-size-fits-all approach. Now, if you're pouring a small pathway in your backyard, this prescriptive method might be perfectly fine, but it completely ignores the specific dynamic properties of your actual local ingredients. So what happens when you try to scale this up? Well, looking directly at the IS 456 engineering code, you can see how nominal mixes completely lock you into strict limits. Let's say you want an M20 grade concrete, meaning a mix that can handle 20 megapascals of pressure. The code dictates exactly 250 kilograms of dry aggregate and a strict maximum of 30 liters of water per 50 kilogram bag of cement. There is zero flexibility here. It doesn't matter if your local sand is exceptionally fine or your crushed stone is already soaking wet. The recipe is the recipe. And here is the massive flaw with that kind of rigidity. To ensure the concrete doesn't fail, engineers end up overcompensating. Because you can't trust the exact properties of the local materials, the nominal mix intentionally overloads the formula with cement just to create a safety buffer. Now, cement is by far the most expensive ingredient in the mix. So by relying on nominal mixes, you're frequently wasting massive amounts of expensive cement just to blindly guarantee a baseline strength. It's economically and environmentally a huge waste. All right, Section 3, the design mix, the scientific method. This is the real game changer. The IS 456 engineering code explicitly mandates that design mix concrete is preferred. This marks a pivotal shift in the industry narrative, moving away from culinary guesswork and towards strict statistical standards. The code outright states that if you fall back to nominal mixes, you're going to be penalized with a higher cement content requirement. The standard has officially evolved, and codes now demand we treat concrete as a highly engineered product. By replacing a prescriptive recipe with a performance-based formulation, the design mix treats concrete as a dynamic, adaptable material. Instead of starting with fixed ingredients, you start with your end goal, the exact required strength, durability, and workability. Then you test your actual local materials. You test their specific gravity, their water absorption, their fineness. And finally, you custom tailor the precise proportions to hit that exact target with absolutely zero waste. Now consider the single very specific number, 1.65. This is the Hemsworth constant. It represents the standard deviation multiplier used in rigorous quality control, and it's essentially the secret weapon of the design mix. It proves that we are no longer just guessing, we are using hard statistical probability. Instead of crossing your fingers and hoping for the best, the design mix uses this statistical formula as a risk management tool. Out in the field, concrete strength varies naturally on a bell curve.
We don't just design for the bare minimum characteristic strength. We design for a target mean strength that is intentionally pushed higher by exactly 1.65 times the standard deviation of our materials. We are mathematically programming our quality control right into the formula to ensure a 95% success rate.
Section 4. Designing the perfect mix. Steps to success. The procedure flows through some very clear scientific steps. You establish the target strength, you calculate the critical water-to-cement ratio, and you rigorously test the aggregates. Whether you're using the American Concrete Institute method, the British DOE method, or the Indian Standard method, the core philosophy is identical. You analyze absolutely everything. Does the aggregate absorb 1% of the water? Does the sand have 2% surface moisture? Every single drop of water is meticulously accounted for. But all that advanced math has to ultimately be grounded back into physical reality. That's where continuous on-site testing comes in. Engineers measure the spread and slump of the fresh concrete because, let's be honest, a perfect design mix on paper is totally useless if it's too stiff to pour or too watery to hold its strength. We use these physical tests to confirm that our mathematical design behaves exactly as predicted out in the real world. This incredible level of statistical control is exactly why modern ready-mixed concrete plants rely 100% on design mixes. You simply cannot operate a modern transit mixer fleet using rule-of-thumb recipes. They use highly automated, computerized batching plants to weigh out the precise grams of water, cement, and chemical admixtures to guarantee flawless performance, block after block, truck after truck. Which brings us to our final section, Section 5. Why design mix wins, the ultimate verdict. The crucial takeaway here is that the design mix wins because it saves massive amounts of money by optimizing cement use, and it mathematically manages structural risk. But even more importantly, it is strictly required by code for any high-performance concrete above M20. If you are building a modern high-rise or a bridge, you're using M30, M50, or higher grades. At those levels, the code strictly outlaws the nominal mix. You simply aren't allowed to guess when the stakes are that high. So it leaves us with a pretty provocative thought. In an era of towering mega infrastructure and advanced quality control, the days of simply baking our buildings are well and truly behind us. When we have the mathematical tools to optimize our resources, save money, and guarantee safety to a 95% statistical probability, going back to the old rule of thumb isn't just outdated, it's irresponsible. The next time you walk past a construction site, you'll know that the gray material being poured isn't just a simple mix of rocks and paste. It is a highly engineered, mathematically perfected scientific formula.